right. Why am I in this? Sorry. All right. So here we go. So where did the atmosphere come from? All right. Um, if you take the gases that come out of the earth from volcanic activity, that does not account for all that we find in the earth's in the atmospheres plus the oceans, especially the oceans. Um, and so some people realized, hey, well, wait a second. Over the course of 4.5 billion years, there's been lots of things that have struck the Earth. For example, asteroids. Asteroids have hit the Earth. They could have deposited some gases, and some water vapor as well. And also, and a little bit later, we figured out that comets contain mostly water. As a matter of fact, that's basically what the comets are made of. They have other gases as well, but mostly water. And so the modern theory of where the atmosphere and the oceans come from are actually impacts with comets and asteroids. All right. There was, of course, there's always been volcanic activity. Whenever there's volcanic activity on the Earth, there is some water and some carbon dioxide and some nitrogen that comes out. But the asteroid impacts and the comet impacts have added to that in the amount of these molecules that we find on the Earth today. Right, like even if you estimate the amount of volcanic activity over the course of 4.5 billion years, you don't get the amount of carbon dioxide and water and nitrogen that exists on the Earth. So it had to come from somewhere else. And what we now feel, more and more evidence, in fact, is showing us this, is that it comes from impacts from asteroids and even comets. All right, so in the early atmosphere, actually, we think that the Earth contained contained methane, which is this molecule here, CH4, and ammonia, which is NH3. And what happened is, over time, the ultraviolet light, which we think was more intense in the early parts of the solar system when the sun was rather young, and that caused the hydrogen to basically be removed from these molecules, and it left water and carbon and nitrogen and the oxygen really. The oxygen never stays by itself. It always becomes O2 molecules. But anyhow, the oxygen is there. It usually chemically bonds with something else. But the hydrogen, let's say if the hydrogen is removed chemically, electrochemically, I should say. Anyhow, in the early atmosphere, if the hydrogens are removed, the hydrogen can't remain in the atmosphere by itself, right? It needs these heavier atoms to stay and be part of the Earth. If you just had if you just had hydrogen atoms in the Earth's atmosphere, those hydrogen atoms would escape, right? Remember, it's gravity that holds the atmosphere down. So hydrogen is far too light to just to remain. And so over the course of many billions of years, plant life increases the amount of oxygen, right? Photosynthesis, one of the byproducts of photosynthesis, and I said this before, and you probably knew this, is oxygen, the O2 molecule, right? And so life has evolved to use the O2 molecule. It's actually, it's a wonderful source of energy. Anyhow, all right. So let's look at the atmosphere in a little bit more detail. And the reason, then, by the way, the reason that we're going to talk about this is we actually find this phenomenon on other planets as well. So when a planet is spinning rather rapidly, like our Earth does, once every 24 hours, it turns out that the atmosphere and the water, the water will be affected by that rotation, and so that's that rotation, or the effect of the atmosphere, and of course the ocean. The effect of the rotation is called the Coriolis effect. So here's a typical example, right? If you were to launch a missile directly from the Earth's equator, right? So keep in mind we're spinning from the west towards the east. Okay, that's just the normal rotation of the Earth once a day. Right, so we're spinning that way. That's why the sun seems to rise in the east and set in the west. That's of course just because we're rotating in the direction of the east. Right, so we're spinning towards the east from the west. Right, so if you're on the equator, for example, and you were to launch a missile, or it doesn't even have to be a missile. We don't really have to think about missiles, but even an aircraft. All right, so an aircraft going directly due north, right? Just traveling towards the North Pole. Let's say that's its destination, right? It's traveling from the Earth equator towards the North Pole. What's going to happen is during that trip, it will be deflected. The airplane will be deflected towards towards the east, and that deflection is called the Coriolis effect. All right, so that's so sometimes you'll hear people talk about that it's the Coriolis force. It's actually not a force. It's just because you're in a rotating reference frame, and that's the technical description of it. But of course we also see that with in the ocean as well. There's this thing called the Gulf Stream, right, which comes up along just off the coast of the eastern United States, and actually the Gulf Stream is what causes England, Great Britain, to have a relatively moderate winter. Relatively moderate. I mean, it gets cold in England, certainly, but it's not as cold as it would. If the Gulf Stream didn't exist, then Great Britain, it would be much colder in Great Britain. All right, so those are some of the things that happen with the circulation of the air and the circulation of ocean currents. This thing called the Coriolis effect. Well, and of course, this has to do with the direction of hurricanes, right? So think about it, like in the, I don't know, is this the United States right here? The counterclockwise rotation of hurricanes is because of the Coriolis effect as well. Right, so it's just, and of course, when we look to some of the other worlds, there is a great, like way bigger than anything on the Earth. There is a huge hurricane. Well, it's even, you might describe it as a super hurricane, I don't even know if that does it justice. That's of course what the Great Red Spot is. It's a gigantic storm that has been raging for at least 300 years. As far back as the time when telescopes could actually make this out, by humans. And remember, telescopes are barely 400 years years old. Um, now, 400 years ago, the telescopes weren't powerful enough to be able to see the Great Red Spot, but very quickly people started building more and more powerful telescopes to get better looks at things, and once they could see the Great Red Spot, it's been this thing that's been on Jupiter for at least 300 years, probably longer, probably a lot longer. But we also see the Coriolis effect in the atmospheres of Saturn. Saturn, although doesn't have the kind of features that Jupiter does, it's a little bit more plain looking. But we also see some of the Coriolis effect on Neptune as well. Neptune turns out to have some really high winds. We'll talk about that later. All right. Now the Earth also undergoes precession. So now what is this thing called precession? So if you were to spin a top, right? Like just take a top and spin it on a desk and watch it over time, you'd notice, of course, that as the top slowed down, it begins to wobble. Right? Wobbling is the key. In physics, we call that precession. Right? So the Earth is actually slowing down. Believe it or not, it's not slowing down very quickly. Okay, nothing to worry about, but it is slowing down because it gets slightly different gravitational pull on different parts of it by the moon, in fact. And to some extent, the sun is responsible for this as well. And at any rate, it causes the Earth to wobble, and that wobble takes about 26,000 years to wobble around once. So that's the rate of precession, right? And so that has some definite consequences. So where the direction of north, right? Like we're in the northern hemisphere. We look and there's a bright star, and it's called Polaris, also known as the North Star, right? Now, right now in our history, where the Earth is, Polaris happens to line up very close to the north, to the North Celestial Pole. Remember, the Celestial Pole is the extension of the Earth's North Pole out into space, and so this happens to line up. Now, if you were to fast forward 14,000 years from now, there's another bright star in the northern sky called Vega. It's actually much brighter than Polaris. And Vega will be within just a degree or so of north. So thousands of years ago, so this is 4,000 years ago. There was a star, or I'm sorry, this was 2,000 years ago, right? So I'm sorry. Yeah, so 4,000 BC. All right, so in 4,000 BC, so that would 2,000 years ago, and then 2,000 years more. That would be oh no, so that's 6,000 years ago. Sorry, 6,000 years ago. There was a relatively bright star in the constellation Draco, which is this huge constellation that you can see almost every night. Anyhow, there's a bright star called Thuban that maybe not quite as bright as Polaris, but that lined up about 6,000 years ago. All right. So yeah, like I said, in about 14,000 years, which is a long, long time. That's much more than the amount of time in recorded human history, right? I mean, human history, the actual stuff where people started writing stuff down, and we still have access to that stuff, is maybe pushing it would be about 5,000 years old, right? So